Hey everybody, it's Friday here, so it's dress down day. I'm usually wearing a better shirt than this, but we allow everyone to wear t-shirts on Friday. So just about to ship another custom system, and I thought we were so happy with how it turned out that I thought I'd make another video here on custom systems. In this case, a customer came to us. A lot of times customers come to us, they know exactly what they want. We say, okay, what do you want? What are you trying to do? This customer is a little bit more vague. They knew kind of what they wanted. They have an existing system, and what they wanted is a system that will let them do what the existing system does, but be smaller, less power, and smaller and cheaper, and available from the current vendor, not too available these days. So we said, well, what do you want? And they said, well, it's about this big, does about like this, and so they just weren't really clear. And so I said, oh, I tell you what, since you have an existing system, how about if you send us your existing system, we'll fully characterize it, we'll measure the mirrors, and then we'll figure out what it does, and then we'll figure out from there what we can do for you. So what this customer sent us, and it's just completely anonymous stuff, they sent us this. It had mirrors on it, but what it is two Cambridge 6220 scanners with the mirrors that we eventually put on this. So these mirrors were on here. So what we wound up doing was dismounting the mirrors, just like the gymnasts do. We dismounted the mirrors from here, and then we fully characterized those in the computer in terms of the inertia, and we put them into an optical model to figure out what they can do. And in this case, it does 5 millimeters at 80 degrees. It's pretty good. And so this was this. They have two of these servo drivers, two Cambridge Model 671 servo drivers. It takes up a lot of space. So what we do is we do a full characterization on this. What's the step time? What's the bandwidth they're getting? Because they were really happy with all of this stuff. And then, so I'll go through a little bit about what we do in the modeling process, and then what we were able to deliver here to the customer. I'm driving it to FedEx tonight. So what we're going to be delivering, I'll kind of cut to the chase, is this, which is a 20-bit version of our Mach-DSP, brand new. This is for a precision projection application, so they need 20 bits for that application. This is brand new. They're the first one to get it. Very exciting. And this, which is a fully custom scanners. It's fully custom, everything about it. The rotor's custom, the mirror's custom. It's their mirrors that we mounted on there. Front bearings custom. So this is another fully custom system that we're delivering, and should exactly meet their needs. And in terms of performance, I'll tell you about the performance here in a second. And be a lot smaller, because you only need one of these, whereas you needed two of these. And the power consumption is amazingly lower. And part of the reason why is because this particular 671 driver has two power amplifiers, what we call an H-bridge configuration. H-bridge is great when you need it, but we do not deliver H-bridges under ordinary circumstances. We can usually find ways around that with coil configuration. We'll talk about that here in a second. But yeah, so we'll maybe pan pass here. I was just doing some current control loop testing and modeling here on the digital scope and on our dynamic signal analyzer. And then, so the process is, as I say, customer sends us the thing, and we fully characterize what that servo driver did, and so here is, we use that same dynamic signal analyzer. We sweep that servo driver with that plant, and here's what it does, and then we put markers around. We could find the resonances and anti-resonances. But with this, we could kind of really know what the customer's getting, because like I say, they didn't know what they were getting. They don't know what they like it, but they don't know. They can't really communicate it in technical words. So then we go into the computer and we actually model the 6220 rotor with their mirror and the mirror mount, and we can calculate all of the what we call the resonance, the bending mode resonances and torsional mode resonances, and you could see them up here, the first bending mode, second bending mode, and the first torsional resonances presented right up there. And then we go out. The next thing for us to do would be to prospectively design a scanner that would do, that we would believe would do a better job than that. And so here's our prospective rotor that we designed. We put it and we use a software called ANSYS. ANSYS is the best tool to do resonance analysis. And what you can see is the first bending mode, second bending mode, and torsional resonance that we were able to achieve, which in all cases was higher. So in this case, for example, you got 1700 for the first bending mode resonance. In our case, 1887. In their case, the first torsional resonance was 12.7 kilohertz. In our case, it was 12.9 kilohertz. So we were able to do better resonance-wise in all respects. So then what we could do is we go in and we take our own servo driver and scanner development software that we made, and we could say, okay, here we put the Cambridge Model 6220 in there on, let's say, the x-axis, and we put our scanner in there on the y-axis, and now I can compare what their scanner will do and what our scanner will do under similar stimulus conditions, but I can measure the coil voltage, coil current, the heat generation, all this other stuff, right? So we can really do a comparison and we say, okay, yes, this looks good, let's go build it. So that's what we did. So let me tell you that what we were able to achieve with this, which is kind of amazing. Like I say, what they have there is a H-bridge driver, and so you can see the current or the voltage here on that Cambridge would be driving to the scanner. And I actually verified that this is true. It's not just our simulation, which in this case is 10, 20, 30, about 40 volts peak on this. In our case, the green, we have our scanner doing it on the green trace here, which is less than half. So what we were able to accomplish was the exact same position, volt, velocity, everything else, the exact same performance, because customers were happy with the performance, but we were able to achieve that with less than half the coil voltage, less than 3/4 of the coil current, and also we have a lower coil resistance too. So what that means is that we had less than 1/4 of the heat generated at the scanner. And since we were using our not an H bridge, plus minus 24 volts, and they have an H bridge at essentially 48 volts, the power consumption is incredibly low. It's less than a tenth for their particular waveforms that they're scanning. So like I say, we were very happy with what we were able to deliver to the customer, especially like I say, they kind of didn't know what they wanted per se. They knew they were happy with what they were getting, but really couldn't communicate it from a technical standpoint. And so we were able to kind of take it all apart, so to speak, model something completely new, put it all together, and deliver prototypes pretty quickly and pretty cost effectively. This stuff does cost money. We don't do it for free, right? But so the customer does have what we call an NRE charge. It's a non-recoverable engineering, so they pay for our engineering, our time involved in designing the scanner and that sort of thing up front, plus a commitment to buy, assuming that we can hit their performance target, which clearly we did. So that's how it works. So like I say, this is a second video I'm making on custom systems, just to give you an idea of what we can do custom-wise. And so let us know if you have any questions or comments. Thanks.